Okay, let me get rid of this side. Okay. All right. So, yeah, thanks for having me here, Andre, at the workshop. So I'm going to talk about predictive motion models for vulnerable road users. And this is somewhat of an overview talk, and I would like to give credit to my former and current PhD students that are actually doing the work. There has been big progress on environment perception in the context of self-driving vehicles, driven by improvements in sensing. We have high resolution cameras, radars, and LiDARs. We have strong progress in algorithms, mainly fueled by deep learning. And there is a lot of new data coming out there and associated benchmarks. That allows us to not only recover the spatial environment of the vehicle quite accurately, but also increasingly get better at doing semantic scene analysis. And I have here one benchmark that we ourselves introduced last year together with my colleagues at Daimler. It's a benchmark, a quite large and diverse benchmark on person detection, and it involves 250,000 of persons, pedestrian riders. But the main part, it's very diverse. It involves 31 cities across 12 countries in Europe. So that's really nice. There is a download link over here, and there is an evaluation server. I just brought some video to show you what's the state of the art is of single frame person detection, meaning pedestrians in green and some of the other riders in red. And as I said, these are single frame results, and we can also get partially occluded pedestrians. We will see a lady coming from the left, and we can see that we're picking up her quite well. And so that's really nice. But in order to go to the next step, as also was mentioned previously, it's very important to also have this measure of understanding how a scene will develop in the next few seconds. And this will facilitate a driving style that is efficient, that is fast, but it's also comfortable and it's not jerky. So the basic insight is that you would like to adapt. Is it a potential dangerous situation that you might slow down proactively? And in order to make this happen, to have this kind of fluid and adaptive driver style happening, you need one key feature. You need to be able to anticipate what's happening in the scene, and you need to predict what the other road users were planning to do. And so we started on this topic very early on in 2013, and we were looking at pedestrians and just looking at using position information. And it's clearly, if I'm looking at this video, it's from the driver's view. It's very difficult to figure out what's happening, which of these pedestrians will cross. And indeed, in some studies, we showed that we could only detect crossing after it already started. So that would be not very helpful. Then in some later work, we added some additional features, image features, optical flow features, the intuition was that we could actually infer some additional information from perhaps some local deceleration of body parts at the leg region and so forth. And we developed a system that used Gaussian process dynamical models, which would devise latent space and come up with a model in this latent space. And so this was a model for optical flow images in latent space, and we could actually predict in this latent space what the pedestrian would do. In this case, that the pedestrian would actually stop, and so we could continue driving safely. Using this additional information, we showed that we could get the same accuracy as before with only position, but we could get the same accuracy 200 milliseconds earlier, which is very important in the context of intelligent vehicles. But if we're looking at the scene that we saw previously in this reduced representation, and we are looking at this in the actual imagery, you can see there's much more richness in information. And typically, if this would be a live or like a physical meeting, I would ask the audience which pedestrian would stop or would cross at the curbside. But here I will just give the answer. It is, if you take a look at this scene, many people would say that this brown pedestrian will stop because he's actually paying attention, he's at the curbside, and in fact, he's even slowing down already slightly. Whereas this guy, well, it's very hard to figure out what this guy is going to do. He's really far away still from the curbside. He's not paying attention either. We set out back then to develop a system that uses these cues like a human driver would actually do. And so has the pedestrian seen the vehicle? Is the pedestrian at the curbside? And is there any influence coming from the vehicle? Meaning, is there a potential collision happening? And so we did that in a dynamic Bayesian network. And the main intuition is that we have several pedestrian motion models. So we have a set of basic motion models like walking or standing. And we have a switching linear dynamical system. And this switching state M, shown here in blue, will basically at each time instant determine which of the basic motion models is active. And this goes back a little bit to the comment made earlier by the previous speaker on the multimodality of uncertainty. This multimodality in our case is by having several motion models and a switching state. And the the contribution of this work was that we took these context cues that we showed here in this image, and they basically influenced the transition from one basic motion model to the other. So they influence this switching state. And well, this was a bit of the simplified representation or the simplified video we made for upper management. What you see here is anyway that sees the vehicle and at curbside affects the predicted position within 1 second. The more technical insight is in this slide. It's very busy. I'll try to walk you through it. So we have a pedestrian walking from the right to the left. At the beginning, he's not watching, then he's watching and then stopping at the curbside. What we have here is the latent variables of the dynamic Bayesian network, and we have the time axis over here. And for example, if we look at the curbside variable, so these are estimates from the system. At the beginning, it's false because the pedestrian is still far away, but then it switches to white. In this case, means that there's a high probability at the curbside. So the system estimates the pedestrian to be at the curbside. The same thing with the other variables. At the beginning, the system estimates pedestrian has not seen the vehicle, then it becomes true, so it has seen this vehicle, and the situation critical becomes true soon afterwards. And as a result, the motion model switches over here from the walking motion to the standing motion. And if we take a look at 2 snapshots of this sequence, at the case where the pedestrian is still far away, then if we look at the current, this is the current position of the pedestrian, the lateral position, and we take a look at the predictions made at this point by the various models. There are a lot of models here. The LDS is the Kalman filter. But the main point is that all these models predict a straight line, meaning that the pedestrian is likely to continue walking straight because there's no reason why not. Whereas when he comes up to the curbside and he starts watching, then we can see that the context-free models, the Kalman filter, still shows a straight line, whereas the more sophisticated models with this context cues already predict the stopping. That's kind of very nice, and but this was just kind of the prediction in isolation. And last year at the Intelligent Vehicles Conference, we put this prediction component also together with motion planning and control, and we had kind of an integrated system. So here we have the case that the pedestrian is not watching, and so the car will execute ahead of time an anticipatory evasion maneuver, and we will take a view of what the system thinks is happening and see the circle denotes the orientation estimation of the head, and this red line shows the maximum likelihood ahead orientation pointing to the left for many cases, meaning not towards to the vehicle. And so here we had the latent variables. So here we look at the case where the pedestrian is starting to watch, and as a result, the car is not very influenced strongly about this pedestrian. This is a typical traffic situation in urban environment. So there is a different way of handling this type of information. And we can see that in this case, the latent variable has seen vehicle goes high, meaning the system believes that the pedestrian has seen the vehicle. So that's nice. We extended this approach also to not only represent the pedestrian, but also the vehicle. So we can actually also model the vehicle path by a dynamic Bayesian network and use as context cue whether the driver has seen the pedestrian himself. And these two Bayesian networks are connected or coupled by means of the situation critical latent variable. And we went on to also apply the same method, because it's a very generic modeling method with the DBN, to other cases like cyclists that are turning to the left potentially based on gestures or based on the existence of an intersection. So we know the fact that there is an intersection and a certain cyclist might turn to the left with or without hand gestures. So that's very nice. And the fact is that we are using, for the better or worse, we are using expert knowledge here, because we design this DBN structure ourselves. We have the advantage to have few parameters. It is quite interpretable because we can inspect the latent variables. So this is very good, especially for the vehicle context. But we do have quite a larger annotation effort per training sample, because we need to, this is supervised learning. We have to tell the system in which basic motion model mode it is, whether it's kind of turning or going straight and all that. And all that stuff needs to be annotated in this type of work. Whereas in some other popular approach with recurrent neural networks, we have no expert knowledge. We have many parameters. We can't interpret it, but certainly we don't have to do this annotation effort. And so the question is, how do these two models perform on a same application? And this is what we kind of examined in a recent conference paper. And I'm just going to go straight to the point. What we're seeing here is the DBN, and we see here various versions of the recurrent neural network. And the recurrent neural network gets actually the same features presented to it as the DBN. So basically these context cues are provided to both models. And we're looking here at the log likelihood, meaning that higher values are better. And what we're seeing that the recurrent neural network, with all the features that also the DBN gets a much better, higher log likelihood. So it has the better performance. It's a bit surprising because we had a quite small data set of less than 100 sequences that already we see an outperformance of the recurrent neural network. But I think it's important to try this out again on different data sets to see if it actually also generalizes. But in general, people have found on average a better performance of the RNN-based approaches versus the more handcrafted scenarios. And so I talked about dynamical systems, the various LDS, switching linear dynamical system Bayesian networks, the nonlinear regression component. There are two other categories on trajectory learning and on the agent-based modeling that was also mentioned in a previous talk. And this is some of our work in this area. Orthogonal to that, you can take a look at the motion cues. that are being used. So evidently position and velocity are very rudimentary and informative cues, but as we have seen in this application, the head orientation, the body orientation, and also more detailed things like articulated pose is very important. And then you can figure about the value of attributes. Certainly the motion model for an elderly person, or at least the parameterization of a motion model for an elderly person will be probably different than for youth. And finally, there is also the effect of the environment, like the static environment or the dynamic traffic environment. So there has been a lot of very interesting work happening, especially in the last few years. And Andre, Luigi, and Kai joined forces together with Chris from CMU and wrote last year a quite comprehensive survey on human motion trajectory prediction. We looked into more than 170 papers, so did a lot of reading. And it was not just kind of collecting the references, but really we divide a more detailed taxonomy for prediction models. And we looked at various disciplines in mobile robotics, video surveillance, autonomous driving. And we also looked at the more recent data sets and benchmarking efforts that are involved. So with that, I'd like to conclude, and I think the anticipating the road user motion is one of the key challenges remaining for self-driving vehicles. I presented some of our earlier work on vulnerable road users. I think the trend is clearly to use more context information for motion modeling, which is enabled by better perception and also more detailed map info. What we're still lacking is large data sets and relevant annotations, but I'm happy to see that there is a good progress with the TrashNet in this workshop. Yeah, the open questions, the jury is still out on how much handcrafting should there be versus learning everything end to end. If we're handcrafting, what motion cues and models to use? What about the ethics of handcrafting things? And regarding the end-to-end systems, you know, things like explainability and also stability, actually, which is a very important aspect in terms of functional safety, and overall how to scale up to big data and what annotations are needed. So this is a very active and rich research field, and I think there's going to be a lot of work still to be done. And I'd like to conclude with a quote of Anonymous: prediction is very difficult, especially about the future. Thank you very much.
Thank you, Dariu. This was a wonderful talk. There is one question in the chat. How do you think this DBN model can be extended to multiple humans interacting with autonomous vehicles?
Yep, that's a very good question. Clearly, at this moment, well, one way of doing it would basically to extend the state space, so to have basically all possible combinations, to kind of have it as one super state in terms of pedestrian. But certainly, I think the question is how scalable is this, whether this approach scales in terms of the exponential or not, with respect to the number of pedestrians and the number of queues. I don't know the answer yet, but it's a very good question. I think that there would be ways to simplify things, to kind of only consider one or two pedestrians closer to the vehicle, but you will have to make up some approximations, I think, in order to make this approach scalable.
Okay, and there's another question just showed up. How does the model translate to other dynamic objects like dogs?
Well, I mean, you could learn, so these models are learned from data. And so, you know, you could have a lot of dogs run over the streets. But the thing is that these are systems where there's a lot of expert knowledge, and so the question is, indeed, is this scalable, this kind of expert knowledge, to all kind of objects that might be running around? And maybe what you want to do is to use these models only for some important objects, maybe for pedestrians, cyclists, and cars, and have for all the other road users or cows or whatever, to have a bit more generic motion models and obstacle detection.
All right, maybe one final question, another one on the chat. What do you think about the future of predictive motion models in the next 5 years?
I think it's going to be a great research field, and I think that as I tried to show on this last slide, I mean, the jury is very much still out on what kind of motion models to use for what applications to use, what type of motion models, what type of cues to use, how to learn these cues. Are we going to have specific predictive models per country, per city, per intersection? So there's so many questions. How can we scale up to with large data? How to move towards semi-supervised or unsupervised learning? There's so much work still left.
All right, that was a great question and a great answer. Thank you very much. It was a pleasure. And now we switch for the virtual poster session. So to this end, let me show